Okay, hi there, Matt Trom here. Welcome back from your break. This is the second part of our presentation on normalization for down selection. What I just got finished talking about was the introduction of this equation, which is the one that we are going to use in the design course to do our linear normalization. So it's very slightly different from the equation that I introduced in the beginning, and I told you I was going to do this, right? So this equation is the one that's normally used for normalization, and of course, this is the one that we are going to use because it sets a scale from um, 0 to 10, and it allows us to set all of the the concepts that were outside of the viable customer range, the range set by the customer need statement. It allows us to set all those to 0. And so then they ultimately don't get factored into the down selection matrix and hopefully make the concepts that are outside of what the customer wants much weaker in that down selection process. So anyway, we just talked about where all that came from and mentioned just one more time that this equation is actually most similar to thermodynamic interpolation on the steam tables. So more similar to thermo than probably what you did in DML, for example, Design Manufacturing Lab. Um, anyway, interesting. Okay, so let's just move on to the last point here, which is number 5, which is, of course, we're going to plug in our values. These are our x sub I values. That's the data set that we generated right from looking at all the concepts. So we're going to plug those data values in between the best and the worst values into our normalization equation, and we're going to obtain the normalized value of y1 for each concept. So we're going to have an x1, which is the value that goes in, and we're going to have a y1, which is the value that comes out, and that's what this equation does for us, is just convert our non-normalized values into normalized values that we can then put into the down selection matrix. Okay, so having walked through all that, let me now give you guys an example, a simple example of how to do this. Of course, I've said this before. I'm a thermal fluid sciences guy, right, an energy guy, and so I'm going to take an example out of the energy world, which is that we have a product, and this is sort of arbitrary, but a product that has a subsystem that's capable of measuring temperature, and so the customer need for this product is that the product must quickly determine the temperature in less than 2 minutes. Okay, so normally we would take that customer need and we would convert it into a quantitative metric. I've done that on the next slide, which I'll just show you here for a second. So the quantitative metric is going to be measures temperature in less than 120 seconds, and shorter measurement time is better, right? So having come up with that quantitative metric, our design engineers for this particular design problem have gone to the drawing board and looked at all of the various ways that you could possibly measure temperature, and they brainstormed 5 possible techniques, right? So you guys will come up with 12 or more. These engineers probably are being lazy and need to come up with a few more concepts, but for purposes of this example, we'll leave it here at 5. So 5 ways to measure temperature: a thermocouple, a thermistor, an RTD, which is a resistance temperature detector, an infrared thermometer, and a mercury thermometer. And of course, this is an example, right? So I picked each one of these intentionally because they each use a different method, different kind of underlying phenomenon to measure temperature. And so as a result, they have very different thermal settling times, right? So I've got 5 seconds for the thermocouple, 10 for the thermistor, 30 for the RTD, 1 for the IR thermometer, and then 120 seconds for those old style mercury thermometers, where you actually literally have the thermal expansion of liquid metal, mercury, which is measuring your temperature. So okay, so we've got those 5 concepts and the associated values for this particular customer need. So again, I took the customer need, which is the product must quickly determine the temperature in less than 2 minutes, and I've converted it into a quantitative metric, which is measures temperature in less than 120 seconds, and shorter measurement time is better. And so now I can jump into my normalization protocol, and the first thing that I need to do is step one is look to see if there are any values outside of the range set by the customer needs, and those of course get normalized to 0. So what I'm looking at here is quantitative metric, which I've set at measures temperature in less than 120 seconds. And so what we're looking for is that values that are less than 120 seconds are okay and get the check, and values that are greater than 120 seconds or 120 seconds and greater, those get the X mark. So thermocouple at 5 seconds, good. Thermistor at 10 seconds, good. RTD at 30 seconds, good. IR thermometer at 1 second, good. Ooh, okay. Mercury thermometer, 120 seconds, and my metric is less than 120 seconds. And so this one does not meet the quantitative metric that I generated from this customer need. And so this is going to get the X, meaning I'm not going to include this in my normalization. I'm going to give it a normalized value of 0. And now my data set, my data space that I'm going to normalize is across these four other options, right? So I'm going to throw out mercury thermometer in 120 seconds by just giving it a normalized value of 0. Okay, so having gone through step 1, we're now going to pop into step 2, which is to pick the best value, which just arbitrarily in the data set is represented by X max, and I'm going to assign that a value of 10. So I intentionally selected, again, thermocouples or not thermocouples, temperature measurement and settling time, because in a way that's a little bit confusing. It works like a golf game, right? For those of you that play golf, you're looking for the lowest possible score rather than the highest possible score, right? Faster settling time is better when you're taking temperature measurements, provided you maintain an appropriate level of accuracy. And that's what this customer wanted, right? It was faster settling time anyway. So in this case, it's actually the lowest value is the one that gets assigned the best, the normalized value of 10. So in this case, it's actually meaning the infrared thermometer, which has a settling time of 1 second, that gets us up to 10 in the normalized value. So so here's that one. X max is the infrared thermometer with a settling time of 1 second, and we now have to pick the worst value, right? Because we need the upper and the lower ranges for our normalization. So the worst value, which is assigned kind of arbitrarily the variable name x min, that one we're going to assign a normalized value of 1. And of course, that's the longest settling time. And here we have to be careful, right? Because we have 120-second settling time, which is the mercury thermometer, but we've eliminated the mercury thermometer from this normalization because 120 seconds exceeds the maximum bound set by the customer. And so now the RTD, with its settling time of 30 seconds, that's the maximum in this particular set of concepts, right? That is going to move forward into the normalization process. So that's the one that I'm going to select, the longest one that's still within the customer needs. That's going to be my, that's going to be, there we go, my X min. So I've got that here, picking the worst value for X min, assign that a value of 1. That's going to be the infrared thermometer with a 30-second settling time. Okay, so now that we've got X min and X max identified, we've got now going to assign them their normal values. So X max is 1 second, and its normal value Y max is just 10. That's the IR. And then for the RTD, we've got X min is 30 seconds, and Y min is 1, right? The lowest value in the normalization. And we can then jump into step 4, which is to use those 2 points, right? We've got an X value and a Y value, X value and a Y value, 2 points on a line to perform our linear normalization. As I mentioned before, this is the exact same equation that you use to interpolate in thermodynamics. We're just taking literally Y equals mx plus b, right? Here's Y, here's the slope m, here's x, and then these two terms together give us b. So it's literally the slope-intercept form of a line. and we just plug in our data values, the x sub I values, and out pops the y sub I, the normalized values. So we're going to do those, plug in the x sub I concepts for the uh, between the best and the worst values, which we saw in the previous slide, into our normalization equation and obtain the normalized values for y, y sub I for each concept. So I do that here. So here's the thermocouple. I'm going to take my 5 seconds, plug it in right there, and out pops a normalized value of 8.8. I'm going to take my thermistor, 10 seconds, plug that in right here, and out pops a normalized value of 7.2. And we, of course, expect, and this is a sanity check to make sure that you've set this up correctly, your worst value, your lowest value, 30 seconds, that is going to correspond to a normalized value of 1. And then your fastest value, your best value, when you plug that in, mathematically should correspond to a normalized value of 10, right? So if you plug in the maximum value and the minimum value and you discover that they don't come out to 10 and 1 respectively, then somehow you've done the math wrong. It's a good place to kind of do a sanity check. And then, of course, the final thing is the mercury thermometer. It's still one of the concepts. It's not impossible. We haven't thrown it out, but what we do is just assign it a normalized value of 0. It still goes into the down selection matrix, but it goes in as 0. Therefore, this attribute doesn't get weighted or valued at all, and it tends to knock these concepts that don't address the customer needs out of contention for ultimately being selected. So I wanted to just highlight this in red, that Y5, which is our mercury thermometer normalized value, of course, is 0. Okay, so now that we've got all these values, we can populate the down selection matrix. And so I've got kind of, they're basically the same thing, right? But sort of two versions of it here. One where I highlight the values that come from the analysis, right? So 5 seconds, 10 seconds for the thermistor, 30 seconds for the RTD, 1 for the IR thermometer, and 120 for the mercury thermometer. And then here in kind of this reddish color, crimson color, I show the corresponding placement of normalized concept values in the down selection matrix. So my 5-second thermocouple settling time corresponds to a normalized value of 8.8. My 10-second thermistor settling time corresponds to a normalized value of 7.2. My RTD, which of course is the longest at 30 seconds, has a normalized value of 1, the worst value. And the IR thermometer, which is the fastest with 1 second, has the best normalized value of 10. And then, of course, our mercury thermometer, 120 seconds outside of the customer needs specification, gets a normalized value of 0. So that's how the numerical values that you get correspond to the normalized values that you get out of this normal linearization equation. Okay. So that brings us to the end of this piece of it. Having now watched this series of videos, this lecture presentation, you should have enough information to completely populate your down selection matrix, right? You guys did weighting factors in a previous video, and now you know how to fill in the concept row or the concept column and the normalized concept value column. The last thing that you have to do is just multiply the weighting factor by the normalized concept column, and that gives you a weighted normal value for each concept. And then if you sum up those values, you end up with the down selection value for each of your concepts, and the highest value is the one that you want to pursue for prototyping, barring other complications such as discord between different subsystems. Okay, so that brings us to the end of this presentation. Thank you for your time and attention, and I will see you in class. Bye.